Run your thumb across the cooking surface of a well-used cast iron pan, and you will feel a dark, glossy, completely frictionless finish. This slick surface is often attributed to liquid oil soaking deep into the microscopic pores of the metal over years of use. In reality, that sheen has lost the properties of oil and grease entirely. This surface is a solid, structural sheet that has been grown directly on the iron. You produced this material on your stovetop through a chemical reaction that transformed a liquid into a permanent bonded solid. This transition requires only 3 specific inputs: a standard cooking lipid, high thermal energy, and bare iron. Cooking with cast iron functions as high-temperature material engineering, using the stove to synthesize a frictionless surface from scratch. To understand how a liquid transforms into a hard solid without simply evaporating, we have to look closely at the oil itself. Every cooking fat is built from a structure called a triglyceride. The vertical spine is a molecule called glycerol, and the 3 horizontal arms are long chains of carbon and hydrogen called fatty acids. The vast majority of the carbon atoms in these fatty acid chains are connected by single bonds. These links are highly stable and chemically unreactive. The potential for change lives in the carbon-carbon double bond. Because these specific carbons hold onto each other with 2 bonds at once, they are under tension. These tense, weak spots function as reactive hooks, waiting for an opportunity to break open and link adjacent fat molecules together. This raises a logical problem. If these double bonds are the necessary hooks to build a solid network, an oil that lacks them should fail to season a pan. This is the mechanical failure point of saturated fats. Fats like coconut oil or lard are saturated with hydrogen, leaving almost 0 double bonds and no way to link. Highly polyunsaturated drying oils, like flaxseed or grapeseed, represent the opposite extreme. Their carbon chains are heavily loaded with these double bond hooks. This chart displays the metric food chemists use to measure those hooks, the iodine value. It ranks oils by their polyunsaturated percentage, placing flaxseed at the top and coconut oil near the bottom. The test works because iodine specifically reacts at those exact double bond sites. A high iodine absorption mathematically proves a high concentration of reactive hooks. Selecting an oil is a materials science calculation. A high iodine value dictates the oil's maximum potential to form a tough, continuous polymer. Even with a high iodine value, the double bond hooks remain dormant until they receive enough activation energy to spring the trap. Professional kitchens generally teach that cooking oil should never be heated until it smokes. While smoking oil degrades the flavor of food, pushing the lipid past its smoke point is a thermodynamic requirement to initiate the solidifying reaction. As the temperature climbs toward 500 degrees Fahrenheit, the thermal energy becomes intense enough to crack those tense double bonds open. As the chain fuses, the broken bond leaves behind an unbalanced, desperate carbon atom called a free radical. It lunges at a neighboring fatty acid chain, fusing the 2 molecules into a single structure. The surface of the skillet provides a second, crucial trigger for this fusion. Bare iron atoms readily give and take electrons, acting as a chemical catalyst that accelerates the formation of those early free radicals. Because the iron actively participates, it anchors the very first layer of the growing structure directly onto the metallic substrate. The film chemically grips the pan, preventing it from flaking off. Extreme heat and bare metal provide the thermodynamic trigger and catalyst needed to launch the molecular assembly. Once the first free radical forms, it triggers a self-amplifying domino effect called autoxidation. The act of one radical grabbing a neighboring chain creates a brand new free radical further down the line. That radical lunges for the next molecule, cascading through the film. This cascading event fuses thousands of separate liquid fat molecules into one enormous, sprawling solid sheet. To keep this chain reaction moving, atmospheric oxygen must permeate the entire matrix. Oxygen molecules bond with the fat chains to form unstable compounds that continually throw off fresh radicals to feed the reaction. This requirement for oxygen reveals why the intuitive attempt to season a pan with a thick layer of oil often fails. Many assume that a thick puddle of oil will yield a superior heavy-duty layer. In a thick puddle, the top surface of the oil cross-links and hardens almost immediately. This creates a solid physical barrier that causes descending oxygen molecules to bounce off. By blocking the atmosphere, the deeper oil is permanently starved of oxygen. It never finishes reacting, leaving a sticky, gummy mess trapped beneath a thin, hard shell. Wiping the pan until it appears dry is a strict geometric requirement. The film must be microscopically thin to ensure total polymerization of the entire layer. Over dozens of cooking cycles, these microscopically thin, fully cured sheets accumulate into a solid, cross-linked polymer. This polymer network gradually levels out the jagged, rough, microscopic valleys inherent to bare iron. This inert plastic presents a surface with incredibly low energy. Proteins and sugars struggle to grab onto it, allowing food to instantly release. The surface grown on the stove is chemically a cousin to factory-applied Teflon. This finish also solves the secondary threat facing cast iron, the metal's tendency to trade electrons with water and air to form iron oxide, or rust. The cross-linked polymer film acts as a highly effective hydrophobic bodyguard. The dense solid network physically repels water, blocking atmospheric oxygen from making contact with the vulnerable iron atoms beneath it. Building a non-stick cooking surface and preventing rust are the same chemical defense mechanism. Success depends on a specific formula. Bake an oil high in polyunsaturation, apply micro-thin coats to allow oxygen permeation, and push past the smoke point to trigger the radicals. A flawless skillet is the physical byproduct of a patient, repeatable material science experiment. It's a high-temperature polymer reactor producing dinner as a byproduct.